on programming a chess engine in Python. I'm going to take you guys through setting it up, getting the basics, being able to, get an engine that will recognize what's a legal chess move, what's an illegal chess move, get it to where you can play like a two-player game. And then hopefully have some basic AI, show you guys a couple algorithms that are popular with chess engines. Now, I do want to preface this. This is geared towards simplicity over efficiency. We're using Python as a language. It's not the most efficient. And so we're not going to have a super fast engine. We're not going to be able to look, 8, 10 moves, 15 moves like a lot of the more popular chess engines can. It's just unrealistic to try to do in Python without using some other libraries. So a lot of the design decisions we're going to make in this series are geared more towards simplicity than efficiency. So I just want to kind of preface this whole video series with that. And hopefully we get to a point where you might be able to actually try to change some stuff around where you could make it more efficient. And I welcome you to do that. And yeah, so I want to preface the whole video series with that. Today the focus is just going to be on what's on the screen up there. You see a board, you see pieces on the board, and that's going to be our focus today. So just getting the basic setup of this, getting a display that we can actually work with, so that when we're coding the logic, it's a little bit easier to debug because we'll be able to actually have an interface that we can play with in front of us. So that is the plan. Let's go ahead and jump right in. All right, so I've just got an empty workspace here. here in PyCharm. So you guys can do the same here. One of the things you're going to want to do is to download from Schoology this images file. So I'm going to put that up here. So you'll see today's lesson, and then
In this video, we'll have
and PyCharm. Hello, everybody. I'm looking forward to doing this next video series on programming.
Player has won since no player has played yet.
So we can
programming a chess engine in Python. So I'm going to take you guys through setting it up, getting the basics, being able to, get an engine that will recognize what's a legal chess move, what's an illegal chess move, get it to where you can play like a two-player game, and then hopefully have some basic AI, show you guys a couple algorithms that are popular with chess engines. Now, I do want to preface this. This is geared towards simplicity over efficiency. We're using Python as a language. It's not the most efficient, and so we're not going to have a super fast engine. We're not going to be able to look, 8, 10 moves, 15 moves like a lot of the more popular chess engines can. It's just unrealistic to try to do in Python. Without using some other libraries. So a lot of the design decisions we're going to make in this series are geared more towards simplicity than efficiency. So I just want to kind of preface this whole video series. With that. Um, and hopefully we get to a point where you might be able to actually try to change some stuff around where you could make it more efficient. And I welcome you to do that. And yeah, so I want to preface the whole video series with that. Today the focus is just going to be on what's on the screen up there. You see a board, you see pieces on the board, and that's going to be our focus today. So just getting the basic setup of this, getting a display that we can actually work with, so that when we're coding the logic, it's a little bit easier to debug because we'll be able to actually have an interface that we can play with in front of us. So that is the plan. Let's go ahead and jump right in. All right, so I've just got an empty workspace here in PyCharm. So you guys can do the same here. One of the things you're going to want to do is to download from Schoology this images file. So I'm going to put that up here. So you'll see today's lesson, and then there's this folder, images.zip or compressed folder. You're just going to want to go ahead and download that. And once you have it downloaded, you're going to want to extract those files. And then you're going to want to copy that folder back into your workspace. So over here, we're going to, I have a folder called, or a project folder called chess. I'm going to go ahead and make a Python package. I'm going to name this chess. And I'm going to paste the folder inside of this Python package. Now, if you don't have access to this folder or you want to use your own images, that's absolutely fine. I grabbed some low-res PNG images. I'll also share bitmap. I think I had some issues with some people using Macs and PNGs and reading them in, so I'll also share the folder with the BMPs in them, and you can use that. Now, I just got these off the internet. You can do a Google search for chess pieces and you can download them. The naming convention I'm using for these is lowercase b and lowercase w. as the first letter to indicate what color the piece is, and then a capital letter to indicate the type of piece. So it might be easier to see actually in the folder of the images. Here, we see black bishop, black king, black knight, black pawn. One thing, I'm not sure why I did lowercase p for pawn here instead of uppercase. I don't know. Maybe I should change that right now, but I'm not going to. But if you want to, you can get your own images. One of the things that might be fun to do would be to get a couple different sets of images and let the user actually be able to select what chess set they want. So that could be something fun to do. So I made these transparent. I will share the bitmap ones. I think the bitmap ones are not transparent. So if the PNG works or does not work for you, try the bitmap, see if those work. You could also just grab your own images from the internet and find them. All right. So now that we have the images loaded in, we're going to start with, we could start in one of two places. We could start with the main, or we
can just leave it like this. Perfect. So now we're finished with
we could start with the chess engine game state. We're going to create both those files now. So let's go ahead and create two Python files. We'll call one our chess main, and we'll call our other chess engine. Okay, so let me explain what these two files are going to do. So the main file is going to be our driver file. So it's going to be responsible for handling user input and displaying the current game state information. And I'm going to capitalize game state because it's going to be our class object, say the current game state object. Yeah. That's the main. All right. Now the chess engine file is going to be where we store all this data. So this class is responsible for storing all the information about the current state of a chess game. It's also going to also be responsible for determining the valid moves at the current state. It will also keep a move log. So we'll be able to undo moves, we'll be able to look back at a current game and kind of see how the board developed to that. So these are pretty common things that we would want to have in a chess engine. Now today all we're going to do is store the base of a game. And I'm going to kind of pick it. We're already kind of hemming ourselves in with this design decision. And I'll talk about why I decided to do this particular design. So here we have class game state. We're going to build our constructor here. And basically what we're going to do is we're going to have our main piece of information be stored about the board. And there's a few different ways you can do this. And I know that this is not the most efficient way of doing it, but I think it does have some benefits of ease of use. So we're going to use a two-dimensional list. You could try a couple other things here. One thing I suggest for if you wanted to try to make it faster would be to use NumPy arrays. I think that you're going to get more efficiency when you get into the AI piece of things. As far as creating a player versus player engine, I think there's nothing wrong with this, and we'll be able to play with. We'll be able to see and generate the moves instantaneously. So there won't be any lag or anything like that. But as you kind of play with an engine, and you have the engine creating moves and searching the board for moves, it might take a little bit more time. So, all right. So what is this board going to look like? Well, it's going to be a list of lists, and each list is going to represent a row on the chessboard. So we're going to look at it from White's perspective. And each of these is going to be a 2-letter string representing the pieces. And I'm going to do it the same way that I named the pieces. So here we'll have, in the top left corner of the board, a black rook. Next to the black rook will be a black knight. I'm using N for knight and K for king. Another, if that annoys you already, king and black, that we can, remember what decisions we're already making. So the board is an 8x8 2-dimensional list, and each element of the list has 2 characters. The first character represents the color of the piece. B or W. The second character represents the type of the piece. And here we could have king, queen, rook, bishop, knight, or pawn. And then our last note is that the string, empty quotes, represents an empty space with no piece. Okay, so at this point, we have actually enough to start drawing our board. We're going to add other fields in here later on. So, for example, we're going to have a field that determines whose turn it is. So is it white to move or black to move? We're going to have a field for the move log. So a list keeping track of what moves have currently taken place. And we'll talk more about this in the future videos. So for right now, all I really care about is storing the information here. And I could actually at this point evaluate this board and determine what are all my valid moves, and we could start writing that, given that it's white's turn. There'll be other things we want to keep track of in board states. Things like castling. Castling's a little bit of a weird move in chess, and we'll have to keep track of whether or not white or black move their king, because if you move your king, you lose the right to castle. If you move your rook, you lose the right to castle on that side. So there's some special rules like that that we'll have to make sure we keep track of. We'll handle all that as we go. All right, so here's just our start for our end. All right, now let's go into our main. And this we're going to focus a lot on the Pygame stuff that we've kind of done before. And so I'm going to go through this kind of fast. If you are not sure of some of the stuff that I type, then maybe you can go back and watch some of the videos that I did on Pygame intro. One of the things we're going to have to do is import our chess engine class so that we have access to the board state, the game state. Here we're going to make our width and height equal to 512. You could do 400 as well if you want a little bit higher resolution or higher definition. Basically, the larger you get, the images I shared with you are not very high res, so we can't go that large. 512 still looks pretty nice, and that's about the biggest I've seen it work, where it actually looks good. But 400 is definitely another good option. And you could go larger if you want, but I think at that point you're going to be disappointed by the quality of the images. You might want to get your own at that point. Here we'll have the dimension of the board. Just keeping this in a variable is kind of nice. Dimensions, the chessboard are 8 by 8. And this might allow us to adapt, this to maybe like play a four. If you've ever seen 4-player chess, it's a much larger board. So here we'll define a variable called square size, which will be our height or our width divided by the dimension. And this will give us a nice valid square size. This is another reason why I chose 512. It's a power of 2, and so when we divide it by 8, it makes a lot of sense. We'll set our max FPS to 15. This one, it doesn't really matter. This is mostly going to come into play for animations later on. And then we're going to have this directory of images, which we're going to use today. Or sorry, the dictionary of images. So we're going to make that a global variable as well. All right, the first thing we're going to do is we're going to go ahead and actually load in the images. So let's we only want to do this one time. That's another thing that I want to point out. Pygame loading images in it's an expensive operation. You only want to load them into memory one time, save them as a variable, and use them. If you're loading images every frame, then you're going to notice that your game or whatever you're making is lagging. And it's because you're executing really expensive operations every frame. So we'll put this in its own function. So load images will initialize a global dictionary of images. And this will be called exactly once in the main. And one of the reasons why I want to put this in its own method instead of just putting this code in the main is if you want to adapt it later on to have your own skins. So if you want to maybe give them the option to pick a couple different chess sets, then this will make it nice and flexible. You always want to think about making your code as flexible as possible. All right, so we call this function load images. Again, PyCharm's complaining. It says that I should call this function this because that's proper Python notation, but I'm a Java guy, so I will capitalize my functions and use camel case. So here we're going to make a list of the pieces, and this I could really do this in a very inefficient way. And what I could do is I could say images white on. That will be our key for loading that image. So I'm going to use the piece name notation that we are using here. And notice that these pieces also match the name of the images. So that's another reason why I chose to do it this way. Well, we can read the 2-character string and we can load the image or select the right image just from that. So this one image will be basically, we're going to use the image pygame image.load, and then we have to select our directory, which is images, and then the piece.png. Now, this is probably not the best way to do this, because then we'd have to do this for each line of code. And anytime you see yourself starting to do something like this, and then you realize I'm going to have to do this 12 more times, you should stop, and you should think, how can I use a for loop? All right, so we can see our pattern emerging here. I just have to basically simply make a variable here, which you could call maybe something like piece. And I have to replace this string here, and I can use just this simple string concatenation here, like that. Okay, and so what am I setting this piece variable to? Well, I know that I'm going to have a list of these pieces. So I'm going to have a white pawn. I'm going to have a black pawn. And it doesn't matter what order you do this in. I'm just going to do this in the same order that I have in my other codes so that I don't miss any of them. White pawn, white rook, white knight, white bishop. Again, this order does not matter at all. We're loading these into a dictionary, so you can put these in whatever order you want. White queen. Okay, so that's all my white pieces. Pawn, rook, knight, bishop, king, queen. And then the same thing for the black. Black pawn, black rook, black knight, aka the dark knight, aka Batman. Black bishop, black king, and black queen. All right, so make sure you have all those, and you've got lowercase b, uppercase for the piece type, except for pawn, because it's bothering me now. All right, now what we're going to do now is we can say for piece in pieces. Images piece equals p.image load. And you can see now I only have to type this once, not 12 times. So anytime you can use a for loop to make your code more efficient, you should. Save yourself a little bit of work. Note now that we can access an image by calling or by using the dictionary, by saying something like, I'll put it in single quotes, images, and then white pawn, for example. So images white pawn will return us the white pawn image, because what we did was we saved the image there. for the piece white pawn in the dictionary with the key white pawn. And so this works very nicely for when we're going to actually draw the images in. So what we can do now is simply grab the square on the board, see what piece is there, and if there is a piece there, if it's not blank, then we can say draw that image, blit that image into that location on our screen. Very, very nice and simple way of doing this. All right. We're going to also add a little bit of in here. Right now, the images are not scaled at all. So let's make sure that the images look good in terms of our square size. So let's go ahead and let's add a transform.scale in front of loading, or encompassing this. So transform form.scale, this image we're loading in, and then we're going to call it square size by square size. Now, you could, if you want to, make this a little bit slow, like less than square size by square size, so it doesn't take up the whole square, you can, but I think it looks just fine. Taking up the whole square and being similar in size. And I think it centers it nicely. I think it looks good. All right, so we've got load images done, and we still got quite a bit to do. So let's keep chugging along. All right, so here, this will be our main driver. And this will handle user input and updating the graphics. So here we go, def main. We initialize our Pygame we normally do. You could also initialize Pygame up here. This is never a bad idea to initialize it first in case, you know, one of your other methods actually relies on it. So for example, like if we accidentally call load pieces before main, then we're going to get an error because we have Pygame in here. So it's never a bad idea to initialize it right away. But in this case, you know, it doesn't matter. The way we have it set up, our main is the only thing that's going to be called. So let's set up our screen variable. Normally do display.setMode, a width by height. And again, if you want to add in like a little user interface later on with some menu commands, or maybe displaying the move log on the right hand side, you could certainly add to this. Add other panels like we've done in other Pygame applications. Let's create our clock. Let's fill our screen with just a background color. I'm going to make it real simple. Just fill it with white. This one will not be really necessary later on because we're going to be filling in the squares with colors, but it's fine. You can leave it in for now just to make sure that everything's working right. Let's go ahead and grab a game state. So we're going to now create a game state object calling our constructor. And so what this does is this calls this initialize this constructor here, and it creates these three variables: board, white to move, and move log. And so now we can actually have access to the board by just saying game state board. So for example, and print out game state board, and let's just go ahead and run code real fast. You can see that popped up the window, but it does print the board down. So we have access to it really, really simply. Nice and simple. All right. Now create a game state object calling our constructor. And so what this does is this calls this initialize this constructor here, and it creates these three variables. To and move log. And so now we can actually have access to the board by just saying game state board. So for example, and print out game state board, and let's just go ahead and run code real fast. You can see that popped up the window, but it does print the board down. So we have access to it really, really simply. Nice and simple. All right. Then now we have to load in the images. And notice we're going to only do this once. So it's before the while loop. As is most of our setup. We have our running equals true variable. Give myself some space down here. All right, and then inside of our while loop, as most of our Python, our Pygame applications have gone, we need to clear this event queue first. Let's add in our quit application and our let's add in our quit application so that we have our running equals true variable. Give myself some space down here. All right, and then inside of our while loop, as most of our Python, our Pygame applications have gone, we need to clear this event queue first. Let's add in our quit application so that we can hit the X and it will close out on us, and then we will call our tick and our pygame.display.flip. All right, all standard stuff that we've been doing. I do want to make a note here. This is something that I kind of have seen and never really read up on. Again, Python's not my main language, but this is something that they teach you really early on that I never really did a lot of. But it's Python convention to do something like this. If __name __equals and then __ main, basically matching our function here, then call main. And what this essentially does, this is more proper notation. So this is what Python or this is what Python recommends doing. The reason you would do this is if you ever import your main in another with an import statement. So if I ever say import chess main, then it won't actually run this function. It'll only run this function whenever you're actually running this particular Python. So it has its benefits to it. All right. And that's all I'll say on that. But if you're curious about this, you can Google this, and there's tons and tons of articles about why you would want to do that. So. All right. Our final two functions today are draw board and draw pieces, and we're going to just organize these into a nice little method, which we're going to call draw game state. So our game state will take two parameters, a screen and a game state object. So we can actually call that here. In our main. And in this game state, we're gonna be calling two helper methods. The first is going to be to draw the board. I don't know if, and in this game state, we can actually call that here. In our main. And in this game state, we're gonna be calling two helper methods. The first is going to be to draw the board. I don't know if board is the right way, but draw the squares on the board. So this function is going to draw the squares on the board. And this function draw pieces, which in this case we will need a copy of the game state, at least the board. So we know where to draw the pieces. We'll draw the pieces on top of the squares. And we can use this method later on for if we want to add in, piece highlighting or move suggestions or something like that. We can add these in later. So we'll just leave that. All right, let's document this function, draw game state. Draws the squares on the board, and actually let's just group this all and say it's responsible for all the graphics within a current game state. So maybe even if the user clicked on a square, we highlight that piece or something like that. So we'll definitely be revisiting this a little bit and adding to it. All right, so these two helper methods here, draw board and draw pieces, are going to be our final two methods for today. The first one, draw board. The second one, draw pieces. So this first one is going to just draw the squares on the board. We could maybe adapt this so that the user could pick what colors they want to use for this. I'm going to use white and gray. I don't actually like using white and black because I think the black pieces, because they're outlined in black, they blend in really nicely with the board, and it's actually hard to see them. So I think a gray highlights them a little bit better. But you can pick whichever colors you want. The draw pieces function will draw the pieces on the board using the current game state's board variable, or we could say game state dot board. So one of the things that I want to point out here is that the order of this definitely matters. We want to draw the squares before we draw the pieces. If we draw the pieces first and then we draw the board on top of that, then we're not going to be able to see the pieces. So the order that we call these in is important. All right. So we've got this first method, draw board. I actually wouldn't mind if you would pause the video and actually attempt to do this yourself. I think it's a nice little exercise if you want. I know you've pretty much just been following along at this point, but I think this is a nice little exercise to be able to do. One thing I want to remind you of is in a chessboard, the top left square is always light. So always, 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 that top left square is going to be light. So if we're drawing this, and this is true even if you're from black's perspective. From white's perspective or black's perspective, the top left square is always light. So if you're just drawing this through rows and dimensions, then this is a good idea. So you could give this a try if you want. Pause the video, see if you can, get this to work, and add a pass here, and then you can run it and see if it's running and see what you get. But I'm going to go through the solution now. So if you do want to do that, make sure you pause it now. All right, so here's my solution. The first thing I'm going to do is I'm actually going to define a list of 2 colors. And you might not have thought to do this, but I think this makes it nice for adapting later on if we want to do different colors. So I'm going to pick white and gray as my colors, but I could certainly switch these up. I just need a light color and a dark color. So the way I did this is basically with a nested for loop. And there's plenty of ways to do this, but I think this is a kind of a nice solution. It's not too many lines of code. And so I'm going to do a nested for loop going through the rows and the columns, again using this dimension variable, which was 8 as a reminder. So for the 8 rows and for the 8 columns, we're starting with a light square. So here, and another thing that's kind of neat here is if you look at a chess board, if you add up the row and the column, and then you divide it by 2, all of the light squares are going to have 1 parity, meaning they're going to be even or odd when you add them up. And all of the dark squares are going to have an odd parity. So they're going to have a remainder when you divide them by 2. And if you don't believe me, look at a chessboard. Think, okay, row 0, top left, 0, 0. If I add that up, that's 0, that's an even number. If I go to the right or to the left, or to the right or down one square, I'm on a dark square now. And that's in either row 1, column 0, or column 1, row 0. Both those coordinates add up to 1. If I move diagonally, I'm at now 1, 1, 1, comma 1, row 1, column 1. And all along that center diagonal, I'm at 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, all the way down to 7, 7. And each of those is an even number. So what I can simply do is I can choose the color based on what is R plus C divided by 2. So if R plus C mod 2 gives me an odd number or an even number, I know what color to pick. And in fact, my light squares, since they're going to be odd, since they're going to be even, I put them here to be a remainder 0. And my dark squares I put to be remainder 1. And so I can access the color by R plus C mod 2. So add up the row and the column, mod it by 2, and that'll give you the remainder. That tells you whether the row and the column sum is even or odd. And then this picks the color, white or gray, based on that. And that'll be my color. And now it's just drawing the rectangle. Pygame draw rectangle on the screen with the given color. And then where do we draw it at? We draw it at a rectangle object. And this might be a little bit tricky to think about, but just remember what we've done before. We're drawing them row by column, column by row, because the column is the X value left and right, and the row value is up and down. So we want to start with column times square size, meaning if I'm at column 0, I'm at 0. If I'm at column 1, then I move over square size. And we've talked about this before, so this shouldn't be too surprising that we're again, and then square size by square size for the dimensions. All right, and so we can test this out, and it looks real nice. Nice chessboard. Beautiful. Just a couple lines of code. And what's pretty nice about this is, let's say I wanted to adapt different color structure. Maybe I wanted to do like a light gray for my light color, and maybe like a green for my dark color. Oh, this will look. Oh, wow, that is very bright. Maybe like a dark. I can change those colors, and I can actually get different color schemes here, light and dark. So you can play around and you can find something that you like. I'm gonna stick with my white and gray. I like that color combo. But if you want something more vibrant, then that's certainly your prerogative to do that. All right, and I know this video is getting along, and thank you for hanging in with me. But we're gonna finish this last little piece here. All right, and it is drawing pieces, no pun intended. So here we're going to do a very similar thing for row in range dimension, for column, and again, I used R and C last time. So maybe let's just stay for some symmetry's sake. Let's use R and C again. For R in range dimension, for C in range dimension, the piece that I'm going to be given, well, how do I access that? It's actually really quite simple. I use GameState board. Well, all right, sorry, I've already grabbed the board here. I've already accessed the board variable and I've passed that in here. So I'm already looking at this list here. Now, how do I access? I want to draw it from the left. I want to draw it from here down to here. So I'm going through row by column. My for loop's going row by column. So I'm looking through this first row here, row 0, row 1, and I'm just going all the way through and going through the columns next. And so this is really simple. Board, row, column, just accessing it like that. RC in our case. Now we have to check to make sure that the piece isn't an empty square. Right, let's make sure there's actually a piece there. So if piece is not this, that means it's not an empty square, then we want to draw the particular piece on here. And so why did we spend so much time getting the images loaded in that dictionary? Well, we have this very nice access that we can do with images in the string. And so I can actually make something pretty cool here. So I can blit, and the image that I'm going to blit is just images piece. And whatever string I'm reading in, I'm going to grab that image. Very nice. Don't have to worry about if it's a pawn, draw this image. If it's a white pawn, draw this image. That would be really messy. This is a really nice way of doing it. All right, where are we blitting this image? The same exact rectangle. Column times square size. Row times square size. And we actually don't need to do the rectangle here. We could just do the dimensions. Column times square size, row times square size, and that will work. And this is going to blit it in proper location for us. Okay. So you can see these are actually pretty nice. One of the things I'm thinking now that, would maybe make this a little bit nicer is we could probably just add this in right here. And you're thinking, maybe why didn't I do that? And because this will work just fine, adding it there. Now, the reason I'm not doing that is because I may want to add in highlighting later. So just think about that. Keeping these as separate, even though it does look kind of silly to go through this for loop twice and draw the squares first and then draw the pieces next. But one of the things I might want to do is do syntax highlighting. And I would want the highlighting to be under the piece but above the square. So that's just a thought. Well, I guess maybe you could do the highlighting on top of the piece as well. So it kind of depends. That's not a bad idea if you do it this way. Keeping it separate, it's fine also. Again, this drawing is only going to be called once per frame. So this little bit of extra going through the loop one extra time, not that big, not that expensive, should not really affect our runtime, because it's on the graphics side of things, and we're only doing it per frame. So yeah, maybe it's a little bit more efficient. You want to make that switch, you could certainly play around with that. I'm going to keep them separate, right? All right, and so now we can see, we run our code, we get the images showing up. It looks pretty nice, I would say. Yeah, it's pretty nice. We can't do anything with this yet, and so that's where we're going to stop with today's video. Just to give you guys a thought on where we're heading next. Next week, we're gonna, in the next video, we're gonna move the pieces with the mouse. That's gonna be our focus. And we're going to just allow any move. We're not going to check to see if the move is actually a valid chess move. So it would be like if you gave a 2-year-old your chess set and they could pick up the pieces and they could just move them wherever they wanted. That is going to be our game Monday. And then later on in the week, we'll also work on undoing a move, keeping track of the move log. Sometimes we want to move our bishop. Let me see if this algorithm. And what's going to happen is after we start this process, so I can call this terminate method. It's going to just, and then, but, yeah. So I think that's where I'm going to wrap up the entirety of the series. A couple things to think about.
People who work with statistics and machine learning often run into a recurring problem. What is the best way to analyze a given dataset? By choosing a method that closely models the processes that
Hi, next topic is greedy method. This is one of the strategy for solving problems. Just like divide and conquer and the other strategies, greedy method is also one of the approach for solving a problem or a design which you can adopt for solving similar problem. The problems which fits into this one, you can solve all of them. Let us understand what this method says. What is this method about? This method is used for solving optimization problem.
Well, welcome everybody. I'm super excited for this. Let's dive right in. This is a project that I was working on over the summer. I was absolutely fascinated by AlphaGo and AlphaZero, and had the opportunity to implement it from scratch, and I learned a ton. And here's a lunch and learn to just share some of my experiences.
Onto the Windows Surface with a much Pygame, along with some other low-level frameworks, have had a bit of a resurgence lately. In fact, the winner of the last Ludum Dare, one of the biggest game jams out there, was using Pygame. Pygame has frequently appeared in the top placements recently, including one of my own games. With a lot of more experienced developers showing interest in Pygame now, I figured it'd be a good time to make a tutorial/overview focused on summarizing what Pygame is and what features are in its API. Some of you more experienced developers may be able to watch this video, then jump straight into making full games with Python with just a little bit of help from the docs. So let's jump into it. First, Pygame is not a game engine. It handles basic graphics operations for 2D games, input, audio, window management, and a few other things. It does not, for example, have built-in physics, particle, or even camera systems. Most of the graphical legwork is done by simply putting an image on the screen at given coordinates. Most games are primarily built from functions like these, so you have to be creative about how you use these features. It's also worth noting that Pygame primarily renders on the CPU, which means that there's not a whole lot going on under the hood, and the render calls are super simple. But the drawing performance isn't quite as good as what you'd get with OpenGL. It's more than sufficient for most 2D games though. See my performance video for more details on that subject. To install Pygame, just install pygame-ce with
out, and maybe I'll post some of these in the script. Hello, everybody, and welcome back to part 2 of our test video series. Today, the goal is to get well, let me start with where we left off. We left off yesterday with this sort of window here where we have all the pieces drawn. We have the checkerboard pattern, so we can now start to play chess. But clicking on stuff doesn't do anything. So today, what we're going to do is try to handle user input from our mouse. So it should look something like this when we're finished today. Where now you can click on a piece, you can click on a square, and you can move the piece to that square. And if you have two people that know the rules of chess, then they can pretty much play using this user interface, but they can also play like a toddler, where they can move the piece wherever they want, even making multiple moves in a row, being illegal moves. White doesn't have their king anymore. It's fine. It's not real chess. It's like toddler chess. But that's the idea. And then we'll worry about adding in logic for making sure the moves they make are valid. But right now we're just going to handle the mouse input, get the two squares the user clicks on, and make a recording. All right, so let's go ahead and jump right in. So where we left off yesterday, we had our main class that handled loading in the images, drawing the game state, drawing the board, drawing the pieces, all that good stuff. So we've got a lot of UI. And you can imagine where we're heading today is right in this event queue, where we can handle the mouse events. We're going to have to add a little bit to our chess engine. Namely, what we're going to add today is a move class in order to make said move. We actually need to keep track of two squares: the starting row and starting column, ending row, ending column. And we're going to use a class for that. And we don't have to necessarily use a class. You could just continually keep track of like a list of coordinates, basically, of first click, second click. And you don't have to make a class, but I think making a class makes it a little bit easier for us to I think it's a good abstract. It makes it a little bit easier for us to program when we can just set. So let's go back to the main and let's go into our event queue here. Right in here after running false. And we're going to start by putting in the mouse event handles. So if you'll recall from our earlier Pygame coding, we've done mouse clicks before. We look at the event type is, and here we're just gonna do mouse button down. Now, there are some engines, like if you play online, a lot of engines will let you click and drag the piece to the square that you want to move it to. We could add that functionality in, and maybe that's something that we'll add in on a later date. But for right now, we're just gonna simply have the functionality where we click a piece and we click where we want it to go, and it goes there. So we'll keep it simple. It's the simplest way to do the logic. Again, we could make it a little bit more complicated, and maybe that's something that you want to try on as well. All right. So we have this location where we're going to keep track of the mouse X and Y coordinates. Get position. This is the XY location of the mouse. If you do add a side panel in here, then you do just have to make sure that when you're dividing by square size in this next few lines of code, that you're keeping account for like the side panel or the bottom panel. So if you're going to add extra stuff to your display or a border or something like that, you just have to make sure that the mouse location is relative to those new set of boundaries for your board. But since our board is the entire screen, we don't have to worry about that. It keeps it really simple. So the mouse column will, you may want to pause and think about We've done this a couple times before, so maybe you can remember. Hello, everybody. Here for another video into our chess engine. Today all right, welcome back, everybody. I'm gonna move on to the next part of our chess engine. In this video, I'm going to Alright, hey everybody, welcome back. In this video, I'm going to take you through looking at our AI. Alright, welcome back everybody. To those new set of boundaries for your board. But since stuff to your display or a border or something like that, you just have to make sure that the mouse location is relative to those new set of boundaries for your board. But since our board is the entire screen, we don't have to worry about that. It keeps it really simple. So the mouse column will you may want to pause and think about we've done this a couple times before, so maybe you can remember how you would get the row and the column that the mouse is located in on the board given its X and Y. See if you can remember how we did that. And if you recall correctly, it was we took the X coordinate of the location and divided it by square size. Square size being this height divided by dimension. So all the squares are equal size. We do double divides to round it so we don't get an error later on with the draw. And location 1. Square size. Actually, I don't know if we're going to be using variables to draw, so you could probably get away with single divides as well. But. So this will give us a row and a column. No, I take that. You definitely need double divides. We need these to be integers. Okay. So the column and the row of where we click, now we know what piece we selected, basically. And so we're gonna use a couple variables here. So the tricky part here is if the user clicks on a variable and we store that in row and column, but then they click another piece and we store that in row and column, we have two variables trying to do two jobs. As in we are trying to keep track of where the user clicked first and then where they're trying to move the piece to. But if we only have one variable for that, one row variable and one column variable for that, we're going to run out of, we're going to forget the first space the user clicked on whenever we remember the second space we clicked on. And so, there's a bunch of different ways you could do this, but an easy way that we can do this is just to create we're going to use two variables here. First off, I don't want to keep track of a row and a column. I'm going to make it a tuple and call it square selected. So I'm initializing these variables up above the while loop so that we can continuously reuse them, and they have the scope of that is located in the entire while loop. So we're going to not just use them inside this if statement, but we might use them, in a couple different if statements. So we're gonna keep it out here, and basically I'm starting off with square selected being empty. No square is selected initially, and we can also use this later on for syntax highlighting. But this will simply keep track of the last click of the user. And it'll be a tuple, meaning it's going to be a row and a column like that. A little more clear. And then we're going to have another variable, which I'm going to call player clicks. And this will be just a list, but it's only going to have 2 elements. Or up to 2 elements. It'll have 0, 1, or 2. And this will keep track of the player clicks. So it will have basically 2 tuples. And so we can imagine that this is going to look like, for example, maybe the user clicked on row 6, column 4, something like this. This would be one of 7. 4, this would be one of White's pawns. Oh wait, no, 7 would be the back rank. Yeah. See, this is why we use rank file notation. It's easier to visualize than this row column notation. And then maybe we're moving that pawn up 2 rows, so maybe to something like that. And so when the user clicks on square 6-4 and then clicks on square 4-4, player clicks would look something like that. So hopefully that makes sense. Now, what we're going to do now with this information that we have is we're going to just store it in this square selected variable. So we're just going to store row column as a tuple in square selected after we click on a square. Now, here's the thing about this. What if the user clicks on the same square twice in a row? Essentially, what it would be telling the computer is move this piece to its own location, and we don't want that to be the case. We don't want that to be a valid move. Oftentimes, when you click on something, you're kind of highlighting it. When you click it again, you're unhighlighting. You're deselecting it. So the first click is a select, the second click is a deselect. So what we're going to do actually here is we're going to check to see if the user previously selected this square. So we're actually going to, before we assign square selected to this row column, we're going to actually check if it's already equal to row and column. So this basically means the user clicked the same square twice. And this is typically an undo action. That's what we want it to be. And so if that's the case, I don't want to set square selected to row column. I actually want to unselect it, which is setting square selected back to empty. So deselect or unselect. And in that case, we're also, in case we had previously saved player clicks, we'll also reset and clear the player clicks. And it's basically just restarting that. Hopefully that logic makes sense. Now, let's say they do make a valid click, and so this would be, in other words, they are selecting a different square than they previously selected. Then we'll keep track of that square. And what we want to do with that, so if it's the first click or the second click, we're going to append it to our player clicks list. And so now, if it's the first click, then it'll append to the first object. If it's the second click, it'll append to the second element in the list. And so we'll have up to 2 tuples. And so we append for both first and second clicks. So now we at this point we have to ask ourselves the question: was that the user's second click? And if it was, then we want to do something. So here, if the length of the player clicks is equal to 2, meaning this is after the second click. If it's after the first click, then we're just waiting for them to click the second time, and we don't do anything. If it is after the second click, if length of player clicks equals 2, now we want to make a move. Now we want to tell our engine, hey, here's the squares the player wants to move. They want to move the piece on this square to the piece on this square, and can you do that for me? And at this point, we have to make another design decision. We have to decide how we are going to make the board play the moves. And we also want to keep track of the moves so we can later undo them. So there's definitely a few decisions we want to make here. What I'm going to do is make a move class. You don't have to do this with a move class. You could simply do this with pairs of tuples, update the board accordingly. I think it makes it a little bit more clear to create a move class, store all that information in a move class, and then you can do something like writing a chess notation method that will take squares and create the chess notation. So we're going to do a little bit of that. So simply said, what we're going to do is we're going to create a move class, and we're going to do that over an engine. We could do it in the main, but I think it makes a lot of sense since it's going to be kind of tied to the behavior of the game state. Game state's going to have a move log with a bunch of moves. It makes sense, I think, for the moves to be in that class. So let's go ahead and do that. Now, Python does have capabilities of doing something called a nested class, which would look something like this, where you can see this class is inside of this game state. It's not recommended, generally speaking, to do something like this, unless you have a reason behind doing it. And in this case, we don't gain anything from doing this, and we're also there's not really a purpose behind doing this for this particular project, and so we're not gonna do that. But if you're curious about nested classes, you can look that up, and there are some uses for it. But we're just gonna keep them in the same module, Chess Engine, just to make sure this is unindented. So what is this class going to look like? Well, a move in chess is, let's start with our constructor like we do for classes. A move in chess basically has a start square and an end square. And we're also going to pass in the board, that the current board state, if you will, because we are going to want to validate the move to see if we're going to want to make sure that the moves we're making are valid moves. And so we do want some of the information about the board, although our Chess Engine class is going to do the validating. Passing the board allows us to store some information about the move that we're going to need in order to undo it. When I capture a piece with another piece, I want to store the information of what piece was captured. And that way I know, because I'm not going to be saving snapshots of the board at each move, I'm just going to be storing a move log and the current snapshot of the board. And so if I capture a piece, now that piece disappears from the current snapshot of the board. If I undo a move, but I only keep track of the beginning and end squares, then I move that piece back, but what do I put in its place? It's a little bit hard to talk through. It's maybe a little bit easier to visualize. But that's the idea. So we do want the information about the board so we can store the piece captured and the piece that's doing the capturing, so that we can undo the move later on. It makes it a little bit easier. All right, so we're going to have those three parameters for our constructor, and we're going to create some variables. So typically when we've done constructors with parameters, we would do something like this. In this case, we're actually going to do something a little bit different. Instead of just using start square like that, we're actually we're going to break this down into start row which will be start square 0. Remember, start square and end square are going to be tuples. And start column. And then we're going to have end row. And end column. And this is just a little abstraction that we're going to make to help us be able to visualize a move a little bit better. So instead of having to think, we're just decoupling these tuples, and so that we can use them more easily. So we don't always have to say start square 0, start square 1. We can just use these other variables here. Again, you don't really have to do this, but I think it makes it a little bit nicer. And then the other thing we want to keep track of is we want to keep track of what piece was moved and what piece was captured. And so think about how you might grab this data from our board. So hopefully you thought, my board is a two-dimensional list, and now I have these variables start row and start column, so I can very easily access the piece moved, and the piece moved is going to be where the start square was at the current board, and the piece captured will be end row, end column. Now, note that we're not actually making the move yet. This isn't changing the state of the board. This is just keeping track of information. So it's saying, here the user wants to move from this starting row to starting column to this ending row and ending column, move this piece and capture this piece. And, this might end up being that string which we put in for an empty square, in which case no piece was captured, and that's fine. But this just allows us to have all the information about a particular move in one place. And so we can store move objects in our move log, and we can see what square was moved, what piece was moved from what square to what square, and if it captured the piece. And later on, we can add in things to deal with like en passant and castling and some of the other like weirder rules in chess that aren't as common. But we'll be doing that in our engine as we generate. All right. Now, another benefit to using a class like this is that we can make a two-string method essentially, or a chess notation method. And I think it's valid to do something like this just for our own sake of debugging. Because this allows us to kind of see what moves are happening a little bit easier. And if you're familiar with the game of chess, you know that everything is in rank file notation, and that's how they transcribe games. And I think that it's beneficial for us to have a method that does that. So here, I'm going to actually just go ahead and copy and paste. And you guys can copy this down. We're going to use some dictionaries here to map a couple things. So, as was described in Ms. McPhillips' video, but maybe I'll just show you a quick thing here. So let's just say that all right, so you can see here I have a chess.com board pulled up. And you can see that the white pieces are on 1, 2, 3, 4, 5, 6, 7, 8 up the board. So white's on rank 1 and 2. So the ranks are called rows, and the columns are called files, and they're lettered A through H. And so instead of this notation that we're using with row and column being like, here is 0, so like the piece at 0, 0 in computer notation would be this black row. But in chess, we would say that piece is on A8, the file that it's on, and the rank. Um, and that's your rank file notation. And so we're going to do something like that in our code. So I wanted to show you that. So this is what right here. These are dictionaries that are going to do that for us. So this one goes from ranks to rows. So it takes the ranks 1, 2, 3, 4, 5, 6, 7, and 8, and then goes to our row notation in terms of matrix of 7 down to 0. So 0 again was the top rank 8. And then here I do a nice little thing, rows to ranks equals, and then I use this notation here with a for loop. There's actually a for loop in here. And this is just a really cool way of reversing a dictionary. So if you ever have a dictionary that maps one thing to another, but then you want to reverse it, this is a pretty cool way of doing it. And so basically what it's doing is for each of the key and values in the items of ranks to rows, it's reversing it and saying, for all the values and keys, or for each key and value, make a value key pair. So it's just flipping it. And then I do the same thing for files and columns. So you can pause the video and type those out. Now, why did I do that? And this is the key here. So we wanna actually make a nice little chess notation for our move. And so that we're gonna add a function down here called get chess notation. And what this is going to do is essentially return the rank file notation. It's not going to be pure chess notation. So if you know whenever you move a pawn, you just say that the square the pawn is moving to. So like when you capture a piece, you put an X in the notation. So you could make this more like real chess notation if you're chess savvy and you like that. This might be something fun for you to do. Here, all we're going to really do is just do rank file notation. So we're gonna get together a string of values for our starting row and ending row. And I'm going to use a little helper method here, which I think is nice, called get rank file, which just takes a row and a column. So this gets the rank and file for one square. And all we're going to do is we're going to say, let's take our columns, convert it to files for our column, and let's get our rows and convert it to ranks for our row. Now, again, in chess notation, you do column then row, you do file then rank, A8, A4, C6, whatever that is. The letter always comes first, which is the file. And normally when we do row column notation, then we put the row first. So it's a little bit reversed, which we see here. And here we're just going to call this get rank file notation on our starting row and ending row. Our starting row and starting column. And then we're going to add it to another call to get rank file. I forgot self. end row. And column. Go ahead and have those. All right. And so this will allow us to actually see what the move is in chess notation. And again, if you feel inclined to, you can add to make this like real chess notation. Ours is kind of just rank file notation. All right. Because there's a lot more logic that would go into that. I don't. All right. So now we have an idea for a move. The next idea is, well, okay, so now that I have a move, how can I make the board take a move and make said? So let's create a function in our engine game state that makes a move. So let's say def make move, and we'll just take in just a move object. This will take a class of move. So now we can say move.start row, move.start column, move.end row, move.end column. And so it might be easy to see what this method would look like. We're basically going to, when you make a move in chess, you take the piece from its starting location and you move it to its ending location. So what does that do for the board? Well, it makes the starting row and column. Sorry, we need to say move. Starting row. Move starting column. And it sets it to an empty piece, because when we move a piece, we leave the square behind it blank. And what it also does is it moves the piece to its ending location. So end row and end column are the piece moved. And this is why we grabbed that when we created the move. And then finally, we can, and that's all you need to do. We don't have to worry about the fact that we overwrote the captured piece, because the captured piece is going to be stored in this move variable. We also don't need to worry about validating these moves at the moment, because we're going to have something that generates a list of all the valid moves and only allows the user to make valid moves. So we don't need to we can assume this move is already valid. And we're going to do that in another. So now we just append this to a move log. And this is, so we're gonna log the move so we can undo it later. Or maybe we want to display the history of the game. And then we switch players' turns. This is pretty important to do for our engine. We want to make sure that if it was White's turn to move, now it is not White's turn to move. And if it was not White's turn to move, now it's White's turn. And so we're just going to simply swap players. Switch turns. And that will make them. So that's a pretty straightforward method. And it's all made possible because we made this move class. It made this nice and easy to understand what we're doing. All right, now we're almost done. We're going to go back to our main, and we're going to now call this, we're going to go create the move object and then call this make move function. And so how do we make this move? Well, we create the move object by using the move class, and the move class required us to pass in a start square, an end square, and the current board. And so our starting square is player clicks 0. Our ending square is player clicks 1, and our board is game state board. And you can see that this move creation is a pretty inexpensive algorithm. We're just setting 4 variables. That's pretty cheap. And then we're just accessing 2 elements of an array, which is also not too expensive. And so creating a move like this is pretty inexpensive, and actually making the move is pretty inexpensive as well. We're not using any for loops here. We're going to be using that logic later on, but we don't, as far as this goes, this is decently efficient. Now we can do something like this just for debugging purposes. So let's make sure that our code's working by, let's get the chess notation for that move, which is why we, wrote that algorithm. So we can actually see it. And then let's go ahead and make the move. Using our make move function. And this is a function within the game state. So we need to say game state.makeMove. And then finally, and then finally, all we have to do is, and this might not seem obvious right away, but we need to make sure that we allow the user to make a second. So let's reset the user clicks. Otherwise, we won't be able to if we don't actually say player clicks equals empty, then the length of player clicks will never do again. We'll just continuously append. I guess we could. We'd have to put the same twice. So. All right. And that should be it for today. So let's go ahead and test it. We wrote a lot of code today, so there might be some typos or something like that. Hopefully not. But here we go. And so we'll test it. We'll click on a piece. We'll see if we can move it, and it moves it. And you can see it prints out the notation D2, D4, meaning we move the D file pawn from the second rank up to the fourth rank here. And now black could make a move, let's say here, knight f6. Again, it's saying g8, f6. Where did the piece come from? Where did it go? And again, if you wanted to, you could make this, instead of saying g8, f6, the proper chess notation would be capital N for knight f6. And so, there's some logic there. White can make another move. Black can make another move, and we can actually play, a game of chess. Right. And so we're getting there with it. And we have all our moves being logged, so everything's looking pretty nice so far. All right, so that's where we're going to wrap up with today. And next on the plate is a couple different things. So we're going to work on recording and undoing the moves next. So what happens if someone makes a mistake and we accidentally do an invalid move like that? Right? The pawn was in the way. That shouldn't be able to happen. And we're playing. We want to undo that move very quickly. Or someone makes a mistake, a blunder, and you want.
create the data, it increases our chances of finding a significant result or making better predictions. When you consider that a company may spend thousands or millions of dollars to create a dataset and you're the one in charge of analyzing it, you best be as prepared as possible to do it. But how can you know what model is best when you don't even have data? The answer is Monte Carlo simulations, which I've previously called the most important skill in statistics. If you're watching this channel, I assume you're interested in learning and doing statistics. By extension, you're probably going to want to know how to do a simulation study too. So in this video, I'm going to teach you everything I wish I knew about simulation studies when I first started as a student. I'm going to guide you through 3 different levels of simulation studies, each one increasing in complexity, and as a result, the things you need to consider when you're developing them. My name's Christian, and this is Very Normal, a channel for making you better at statistics. The best way to do that is to understand the unique and interesting problems that statisticians face. This is one of those problems. To motivate the simulation studies, we'll work through a problem that I struggle with on a daily basis, growing this channel. One of the most important ways to attract attention to your channel is in your thumbnail. Without a good thumbnail, people won't be compelled to click on your video. Let's say that I have 2 thumbnail styles I want to compare, one with my usual style, and another one inspired by popular trends on YouTube. I want to know which one is better, and God, I hope it isn't this one. YouTube lets me run an A/B test which will let me experiment on these 2 thumbnails. Some people will be recommended my video with thumbnail style A, and others will get style B. We'll pretend to do this for a year's worth of videos, about 27 in my case. Since we're considering views, that's a continuous outcome. Comparing things is a classic 2-sample problem. The relevant statistical methods are the t-test, Welch's t-test, and the Mann-Whitney-Wilcoxon test. The problem here is that there's multiple hypothesis tests, and it's not really clear which one will give me the best shot of detecting a significant difference between the thumbnails. This is where the Monte Carlo simulation comes in. If you don't know what a Monte Carlo simulation is, then don't worry. We'll cover it on this first level. In this level, our simulation study is small enough to be conducted quickly on a personal machine, like a laptop or a desktop. The first step in a simulation study is to generate data. Since we're dealing with a 2-sample problem, we need 2 vectors. One to represent the views that style A got over 1 year, and another for style B. For simpler problems, this data usually comes from random number generators that are available in most programming languages. Base R has functions like runif, rbinom, and rnorm that let us sample from the uniform, binomial, and normal distributions respectively. Python has similar functions, but in the NumPy or SciPy libraries, I think. These functions generate data from functions, but in the NumPy or SciPy libraries, I think. These functions generate data from parametric probability distributions, distributions whose shape change with the choice of just a few numbers, called parameters. This means we can easily tune the random number generator just by changing a few values. According to my analytics, an average video of mine receives between 7K and 14K views a week after being uploaded. To make our simulation as accurate as possible, I want to capture this range when I generate the data. Since I consider this to be a continuous outcome, I'll use the rnorm function. I need 27 simulated values for each vector, so I just need to enter 27 for the first argument. The middle of 7 and 14K is about 10.5K, so I'll use this as the mean of the distribution. If I view 7 and 14K as the 2.5 and 97.5 percentiles of the data, then each of these values are 3 standard deviations away from 10.5K. Working out the math, this means that the standard deviation should be about 1200 views, so I'll use that. Once I run this function, I'll get a vector of numbers that represent a year's worth of views for videos that use style A for their thumbnails. I need to do the same thing for style B, but it'll be slightly different. I'll generate the data such that style B increases the average number of views by 600. If we divide this mean difference of 600 by the standard deviation of 1200, it gives us an effect size of 0.5. This is also known as Cohen's d. Effect sizes are useful here because we're working with continuous data. The scale of mean differences depends on the variance of the data. A 600 view difference when the standard deviation is 1200 looks different than the 600 view difference when the standard deviation is 600. This difference is easier to see when the standard deviation is smaller. Talking in terms of effect sizes allows us to control for the variance in the data and talk in more standardized terms. We'll consider this further in later simulations, where we'll look at a range of effect sizes instead. After generating this data, I need to run a hypothesis test on it. This hypothesis test is the second part of our simulation study, a statistical model that we run. What I'm interested in is how well powered a t-test is to detect this specific 600 view difference. In other contexts, this might be a machine learning model. The version of the t-test I want to run is student's t-test, the one where you assume the variance of the two groups are the same. Later in the video, we'll include Welch's t-test, which is the one where you assume that they're different. Students often get frustrated with assumptions like this because it's unclear how it will affect the results of the test. While you might be able to figure it out theoretically, a simulation study can give you a more concrete answer, which is what makes them useful as learning tools. Student's t-test can be implemented using the t-test function in R. By default, it uses Welch's t-test, so we need to specify in the function that we want to assume that the two variances are equal. This is done by setting the var equal argument to true. Once the test is run, I can check whether or not the null hypothesis is rejected through the p-value. In this case, it's less than 5%, so we'd reject the null hypothesis. This particular result makes sense because the two groups are actually different, based on how I generated the data. It'll be useful to store the result of the test in its own variable. Depending on how the data is generated, we could get a different result, and we need to account for this randomness, so we need to repeat this 3-part process many times. To implement that, I'm going to use a simple for loop to repeat this process 10,000 times. This sounds like a lot, but it'll go by quick, at least in this level. I've already written the code for a single hypothesis test. I can just copy into the loop. It's useful to work out the steps of a Monte Carlo simulation before you actually run the for loop, since it's easier to debug. The only thing I need to add is another data structure to hold the results of all the simulations. I'll initialize a vector outside of the loop and then index the specific position in this vector based on the current replication number. Power is the conditional probability that we reject the null hypothesis, assuming the null hypothesis is wrong. This is exactly how we generated the data, so if I calculate the proportion of simulations that reject the null hypothesis, then I'll get an estimate for how powerful the t-test is in this specific situation. This follows from the law of large numbers, where a proportion of events will converge to the true probability of the event if we have a large number of trials. This is the core reason why we need to generate such a large number of simulations in the for loop. By itself, this number really isn't that useful. The goal of our simulation study was to compare hypothesis tests so that we could see which one had the highest power in situations that matter to us. So in the second level, we're going to move towards this goal and lay the mental groundwork for how to do simulations at a larger scale. In its current form, my code stores all of the results into a vector that we can use later to estimate.
So back in 2016, well, welcome everybody. I'm super excited for this. Let's dive right in. This is a Well, welcome everybody. I'm super excited for this. Let's dive right in. This is a project that I was working on over the summer. I was absolutely fascinated by AlphaGo and AlphaZero, and had the opportunity to implement it from scratch, and I learned a ton. And here's a lunch and learn to just share some of my experiences. So back in 2016, DeepMind, which I'm not sure if it was part of Google back then, but the AI research team, they released AlphaGo. And AlphaGo was the first AI that actually outperformed humans at the game of Go. And this was a pretty big watershed moment in the history of AI, because Go has been notoriously known to be this really complex game. And for reasons that I'll describe in just a second, it was really difficult, close to impossible for machines to reach like true grandmaster level performance. And so this threshold was reached in 2016. And Lee Sedol, who's the Go like #1 player at the time, who ultimately lost to AlphaGo, had such a crazy experience in the process of playing. He said stuff like, "It made me question what it means to be human," and even ultimately retired from Go because of this defeat. He just felt that the game would just ultimately be transformed by Go engines. And so it was a pretty crazy time. That was very quickly followed up actually with AlphaZero, which is an AI that basically uses the same exact architecture to solve the games of Go, chess, shogi, and other related games where you can imagine you have perfect information about the state of the board. So the whole board state is known. There's no like unknowns like in poker. For any game that's like that, the AlphaZero structure can more or less systematically solve that game. And importantly, it can solve that game using the process of self-play. So literally just by experimenting within the confines and the structure of the game itself, it's able to learn strategy and reach superhuman performance and really just sort of systematically improve generation after generation. And so when this finding came out back in 2017, I was absolutely blown away. The idea that a system could simply just self-learn, as opposed to AlphaGo the year prior, it was all definitely a watershed moment, but it was definitely trained on Grandmaster Go games. AlphaZero, on the other hand, was able to surpass AlphaGo's performance, but it had no human training data involved inside it at all. So I just found that to be absolutely remarkable. In fact, it actually kickstarted a lifelong obsession of mine where I've just become very addicted to chess. It was literally because of AlphaZero that I got super into chess. And so in sort of being fascinated with this, I didn't really truly understand how it worked. And so this summer I wanted to implement AlphaZero. And so I wanted to do it on a simpler game because ultimately the architecture and the approach is the same across all of these games. So I decided to do it with Connect 4. And so this talk is about how that architecture actually works. So in order to describe how to win or solve games like this, you have to understand first this concept of a tree, natural structure inside of computer science. And basically the way that it works is we represent board positions as nodes inside of this tree. And so the starting position or the root position is up here at the top. And then from this position, there can be any number of moves. And so we represent these moves as arrows over here. And the arrows point to subsequently other positions, and then other positions can have even more arrows. And this process continues all the way down until you reach the bottom of this tree, where we have what's called terminal nodes. So terminal nodes are nodes where the game ends, and it ends with what we call a reward that we denote by this variable called Q. So Q can either be -1 if the game ends in a loss, it can be 0 if the game ends in a draw, and then 1 if it ends with a win. And so you can imagine every game that has a finite structure, like all of these games, ultimately create a finite tree over here that in principle can be enumerated, but this is where it gets a little bit tricky. So our goal as an AI or developing an engine is to essentially find a path from the root node over here all the way down to a terminal node in a way that actually maximizes the likelihood of reward. So maximizes this Q variable down at the bottom. So this is where it gets complicated. For the game of Go, there's actually 10 to the 170 unique Go positions, as compared to about 10 to the 80 atoms in the observable universe. Like this is such an unfathomably large number. Like if you had an entire universe worth of atoms, for every single atom in the universe, you would still be 10 orders of magnitude shy of being able to count the number of unique positions in the board game of Go. So it's just uncomprehensibly large. And that basically means that brute force is impossible. So we definitely cannot enumerate this tree on paper or in RAM or in any computational system, really, right? So instead, we have to explore subsets of this tree or subtrees. And we have to explore those subtrees intelligently. And what I mean by intelligently is that there's certain moves that you all know in board games where it's obvious that the move would be ridiculous. And so it's worth no further exploration whatsoever. And we as humans develop this intelligence or this intuition about which moves are sort of straightforward to discard. And so the goal here is to develop that intuition. To develop that intelligence so that we can quickly discard certain subtrees in favor of other subtrees that are perhaps more promising. And so this process is called tree search, where we literally explore the tree. And for those of you who are familiar with some computer science tree search stuff, the sort of old school methods of AI of like breadth first search, depth first search, you may have heard of minimax or alpha beta pruning. They kind of won't work for trees that are just this large. And that's the reason why it took until 2016 for us to actually beat grandmasters at the game of Go with computers, because our old school methods of minimax and so on just weren't working for this game. And so the alternative approach that the AlphaGo or AlphaZero team took to exploring this tree was this tree search called Monte Carlo tree search, or MCTS for short. And this is really just the crown jewel of AlphaZero. It's this really beautiful algorithm that once you understand it, you're not only blown away by the simplicity of it, but it's just the foundation that enables this kind of intelligence to manifest. And so this talk is going to explore what Monte Carlo tree search is and how it works. But before we get to that, we have to discuss first a simplified version of Monte Carlo tree search, which is called the multi-armed bandit problem, which is an absolutely fascinating problem. And the way this problem works is, let's say you're at a casino and there's a bunch of slot machines, and you've been given some intelligence that some of these slot machines are actually rigged in your favor. And that's to say that their average payouts are slightly larger than the typical slot machine, which on average loses over time, of course, right? But the interesting thing is that you don't know which machines are rigged or how rigged they are. Is it 5 machines that are rigged? Is it 1 machine that's way better than all the rest? So you don't know what the level of riggedness is, I guess you could say. But despite that, you have a finite number of coins, and your goal is to maximize your profit. And the other interesting curveball here is that despite some machines having a sort of on average tilt towards your favor, there's still a degree of randomness to these machines, meaning you can spin a machine, and if the machine actually wins, you don't know definitively that that's a rigged machine. That might have actually been a losing machine, but just by chance, you happen to get the spin that actually won. And the inverse can be true as well, where you might actually lose, and it would be sort of hasty to conclude that single loss actually dooms that machine to being permanently bad, because you might have just lost by random luck, and that machine might actually be the best machine. Right? So there's this inherent randomness still to these machines, but there's an established average win rate for some of these rigged machines, and your goal is to find these machines and then exploit them. And so inherently, this multi-armed bandit problem is this fundamental balance between exploration versus exploitation. And so exploration is this idea of using your finite coin budget to gain information about the riggedness level of each machine. And then exploitation is basically saying, based on the information that you have, let's just exploit the machine that you believe to be the best machine so far. And so it should be clear to you that these objectives of exploring and exploiting are sort of directly at odds with each other. And so our strategy here is to determine what is the appropriate mechanism to actually balance exploration and exploitation. And so let's actually simplify. Let's just say there's a simple case of 2 slot machines over here. And these 2 slot machines have this payout range, and that range ranges from low to high over here. And after some number of spins, let's say you spun the left machine 10 times, it actually produces this payout range denoted by this green X over here. And we call this green X Q hat. And Q is, like we were saying earlier, is the sort of average reward. And Q hat is actually the estimate of the average reward of this machine. Like the actual true reward rate of this machine isn't known to us. Instead, all we know is based on this sample of 10 spins, the average or estimated reward is provided by this Q hat variable over here. And so this machine on the right, let's say we spun it 2 times. It also has a corresponding Q hat denoted by this green X. And you'll see over here that the machine on the right is slightly lower. And so the interesting thing here is that we don't know the true Q of either machine. And so we can represent the true Q actually as a normal distribution that's centered around the Q hat, right? And the width of this normal distribution is actually influenced by N. And so you can see on the machine on the right, because we just have 2 samples, there's far more uncertainty about the true Q level of the machine on the right. And that uncertainty is manifested as this wider standard distribution, wider normal distribution. And the idea here is that the lower the n, the less accuracy there is, and therefore the wider the distribution is. And so we can signify the width of this distribution by another variable that we call sigma. And so based on all of this, the question becomes, let's say we want to play the next coin, the 13th coin over here. Which machine do we pick? Do we pick the left or do we pick the right? If we pick the left, we might say we're biasing towards exploitation because we're focusing on the higher Q hat of the left machine. But if we pick the right machine, we might say that we're biasing towards exploration because the width of this normal distribution suggests that the true Q of the machine on the right might actually be higher than the machine on the left. And so what we do is we actually denote this thing called padding, where we take the Q hat and then we add some padding denoted by sigma, and we get these yellow X's over here. And what you'll immediately notice is that the yellow X for the machine on the right is slightly higher than the yellow X for the machine on the left. And that's to suggest that there's some likelihood that the true payout is actually higher for the machine on the right. So this padded yellow X actually reflects that the opportunity of uncertainty, let's put it. And so we call this opportunity of uncertainty the upper confidence bound, UCB for short. And so you can think of the UCB almost very similar, actually literally identically as a confidence interval in sort of standard statistics, where you have this random variable centered around Q hat, and the yellow X's, or the upper confidence bound, actually gives us an upper confidence interval for where that variable actually might be. So you may have heard of like the 95th percent or the 99th percent confidence interval. This yellow X is literally that. So we're essentially creating some padding, and we're picking the machine that has the highest UCB value. So that in this instance would be the machine on the right. And so let's do it. Let's spin the machine on the right. It actually ended up winning. And so we increased the n by 1. And because it won, the mean Q hat actually increased a little bit. It's still lower than the machine on the left. But then also because the n decreased, the width of our standard distribution actually decreased a little bit. And therefore the amount of padding actually decreased a little bit. But still the UCB value, which is the yellow X, is still higher for the machine on the right. So we'll spin it again, spin it a few more times actually. And you'll see we're slowly starting to win a little bit more. So now it turns out that the mean Q hat for the machine on the right is slightly higher than the one on the left. And this process continues until we reach 17 spins on the machine on the right. And after 17, you have so much more information about the machine on the right that the normal distribution actually tightens such that the UCB value for the machine on the left now in this instance is actually higher. So this is when we switch back to the machine on the left, take a sample from it, and this process continues and continues and continues. And ultimately it concludes with, at some point, at some arbitrary point, you can just stop the process. Here I've stopped it arbitrarily after 631 spins. And you'll see the vast majority of our coins were allocated to the machine on the right. And after this many spins, you can more or less really know that the confidence interval is really tight for both machines. And ultimately this process of using the UCB instead of just using the Q hat or the mean allowed us to balance exploration and exploitation. And through that process, originally, if you recall, our first 2 spins for the machine on the right were actually suboptimal relative to the first 10 spins for the machine on the left. But despite that, we were able to balance exploration and exploitation and actually still infer that this wide standard distribution actually led to some semblance of opportunity, and we prioritized that opportunity and then ultimately after a while benefited from that. And so this process naturally allows you to ultimately just trade off between exploration and exploitation. And the interesting thing here is that this process actually scales. So as you add more slot machines, not just 2, it can be 10, it can be 100, it can be arbitrarily many. As long as you simply select the slot machine that has the highest UCB value, you will inherently be balancing exploration and exploitation. Okay, so let's formalize this. We talked about the upper confidence bound, or the UCB. The UCB is simply the Q hat, which is the average or estimated payout out based on the information that I have, plus some sigma, which is some padding to reflect the underlying uncertainty of my estimate in Q hat. Okay. Now the next thing you'll quickly realize here is that sigma is just some fixed variable and represents standard deviation over here. But how many standard deviations of padding do you actually want to apply is the question. And so what we do is we actually scale this sigma by some constant scaling factor c, right? And you can imagine large values of c create more padding, which bias the system more towards exploration, and correspondingly low values of c reduce the amount of padding, which in turn bias the system towards exploitation. And so this value of c is actually like determining the quantitative trade-off between exploration and exploitation. And we actually have to determine this value of c empirically or experimentally. And there's no sort of one fundamental c that's correct in all contexts. Instead, the value of c is sort of problem or domain specific. So you can imagine that if you have a system where there's a lot of hidden opportunity, large values of c are actually well suited for that system, as opposed to a system where just a small number of samples allow you to quickly determine the true underlying q values, then low values of c are definitely encouraged. And so we have to ultimately determine this value of c. But still, this term on the right here, c times sigma, ultimately is just some padding that we add to the q hat value to create the upper confidence boundary. Okay, so with all of that in mind, let's get to Monte Carlo tree search. So Monte Carlo tree search is a form of stochastic tree search, which is just a big fancy word to say that it's based on simulations. And using simulations, you're able to determine what your optimal move should be. And so let's go back to our tree example. So we have our current position over here. And here I've described a go position, but this can also be a chess position or a Connect 4 position, or really any board game with perfect information. And again, we represent our tree. So here's all of the possible moves from this position. And our objective is to select from one of these moves. And so what do? We perform a number of simulations. And the terminology in MCTS, instead of the word simulations, we call them iterations. So MCTS iterations. And all an iteration does is simulate the game by picking a bunch of moves. And then that simulation ultimately reaches some terminal outcome, -1, 0, or 1. And then what we do is we keep track of the simulation results. And then at the end of performing a number of simulations, we look at all of the moves. So we see a number of simulations have gone through the move on the left, and then a number of simulations have gone through the move in the middle, and so on and so forth. And then we just simply pick the simulation with the highest average Q value. Or sorry, we pick the move with the highest average Q value after performing these simulations. And so let's now use our knowledge of the multi-armed bandit problem in UCB to actually guide the logic of our simulations. And so here's the process of an iteration. So the first thing we do is firstly, moves are just like slot machines. And so we can actually keep track of the Q hat n, which is like the number of times we've played simulations through this move, and sigma, which is, again, the standard deviation that's based on n. So we can keep track of these Q hat n and sigma values for every single position throughout the tree. And then we can perform a simulation, and that process starts off by starting with the top node. And then we look at all of the possible moves that we can play from this top node. And then we pick the move with the highest UCB value. And then we repeat that process. So then that becomes the current move, node. And then we look at all of its possible child nodes, and we pick the one with highest UCB value. And then we repeat that process over and over and over and over again until we get to the bottom here, which is a terminal node. And a terminal node actually has a true or given Q value. So we know definitively whether that terminal node is a win, loss, or a draw. And then what we do is we do this process called backpropagation, which is different than neural network backpropagation, but confusingly, it's the same term. But really what all this is meant to indicate is that this Q value of 1, we effectively go back through all of the moves that led to this terminal Q of 1. And it's as if we hit a Q of 1 on all of these slot machines. So we change the Q hat values of all of the moves that led to this terminal outcome of 1. And then correspondingly, we increment the n of each of the moves. And then we go back to the very top. to this terminal queue of 1. And it's as if we hit a queue of 1 on all of these slot machines. So we change the queue hat values of all of the moves that led to this terminal outcome of 1. And then correspondingly, we increment the n of each of the moves. And then we go back to the very top. And then we repeat this process. Starting with the top again, we now pick the node with the highest UCB value. And because the last time around we picked this middle node, therefore its n is slightly lower. So its UCB padding value will be slightly lower. So maybe this next time around, we might pick a different move. And so effectively what ends up happening is each iteration walks a different path through the tree. And the paths are essentially guided by UCB. So we're trading off exploring new paths to gain new information versus exploiting old paths that might actually be more promising. And so that's it. And so it's a relatively simple process. We simply repeat this process guided by UCB. But if you think about it, we actually run into a pretty critical problem, and that's the cold start problem over here. So for the game of Go, for a given position, there's up to 19 by 19 or 361 possible moves. And so we call this in computer science trees a fan out factor. So for a fan out factor of 361, this is very, very large. And so when we begin, all of our simulations, like all of our moves are equally lucrative. So all 361 moves are just as interesting to us. There's no basis for us to say that this move is better than that move because we have literally no information about any of the other moves. And so because we have no information, the only way to find information is by actually trying moves. And because of the fan out factor of 361, you essentially devolve to breadth first search over here. So it's a pretty pretty stifling issue. And so how do we actually solve this cold start problem? Before we get into the solution, here's another way of visualizing the cold start problem. Going back to our slot machine multi-arm bandit problem, when you first enter into the casino, for every single machine, we have n of 0, n equals 0 for every machine. So therefore the Q hats are all the same and the standard deviations are all really wide, and therefore the UCB values are equivalent. And therefore, there's no basis for us to pick one machine over any other machine. And so how do we solve this problem? Let's use heuristics. So a heuristic is another fancy word, and basically all it is given a position, let's have some function that estimates what the Q value is going to be for this position. So what is the average win rate? Meaning, if the Q value is high, close to 1, that means from this position, almost always we end up winning. Or if it's close to 0, almost always we end up drawing. So QEST is just the estimated Q value from this position. And then the other output of this heuristic function is called policy. So policy estimate. And the policy basically is a probability distribution over all of the moves from this position. And so for all 361 possible moves, we have a value between 0 and 1, where the sum of all of these values sum up to 1. So it's effectively a probability distribution. And the probability distribution represents the heuristics indication of how lucrative some moves are over other moves. So if we have this heuristic, going back to our slot machine example, let's say we have some scanner, and the scanner is able to, I don't know, X-ray look at the internals of the machine, and it's able to predict with some level of uncertainty whether the given machine might be lucrative or not. And so here the scanner has told us that we have a 0.8 policy on the left and a 0.2 policy on the right. So again, these are probability distributions. So what we can do is we can actually scale sigma up and down based on this heuristic policy. And so because we got a higher policy for the machine on the left, we'll actually stretch out its sigma value. And then for the machine on the right, it was lower. So we'll squeeze its sigma value. And therefore the UCBs are going to be weighted towards the machine on the left. And so this is effectively how we can break the cold start problem. We can start off with a heuristic that essentially influences or biases our sigma, and that causes us to focus our Monte Carlo tree search process initially based on the heuristics preferences. And so just to restate this, the UCB is larger for lucrative moves due to the higher sigma. Okay. So coming back to our old definition of UCB, again, it was Q hat plus this constant times sigma. This new version of UCB with heuristics is Q hat plus P times C times sigma. So P, again, is this policy estimate given by the heuristic between 0 and 1 that is
Ever heard Ever heard the term confidence interval and wonder what exactly it means? Let's simplify it. A confidence interval is a statistical range of numbers calculated from sample data that's likely to contain the true value of an unknown population parameters like average height, average weight, or test scores. Using the formula, confidence interval equals to sample mean plus critical value multiplied by standard deviation divided by under root of the sample size. Suppose you want to find the average salary in your city. Instead of surveying everyone, you survey 100 people and get an average of $50,000. A confidence interval might say, we are 95% sure that the true average salary lies between $48,000 to $52,000. The 95 here isn't the chances that true value is in your specific interval. Rather, it means if you did survey 100 times, 95 times the real average would fall inside the range. Confidence intervals help us acknowledge uncertainty, keeping the statistics transparent and honest. Like, share and subscribe if you found this helpful. Also let us know in the comment section which topic should we simplify next. Ever
So far,
Yes, Kumar. So, let me just take that what I can.
நம்ம வந்து என்ன பண்ண போறோம்னா ஆல்ரெடி ப்ரீ ட்ரெயின் மாடல்ஸ் வந்து நம்ம யூஸ் பண்ண போறோம். ஸோ இது வந்து பார்த்தீங்கன்னா இந்த மாதிரி
Maths. வணக்கம் நண்பர்களே. இப்போ நம்ம இன்னைக்கு பார்க்கக்கூடிய டாபிக் பார்த்தீங்கன்னா டேட்டா சயின்ஸ் பார்ட் நம்ம பார்ப்போம். இந்த டேட்டா சயின்ஸ்லேயே இந்த வீடியோஸை
அதாவது நீங்கள் ஹைட்டை ஆட் பண்ணிக்கலாம். இப்போ இதுவும் பார்ஸும் தெரியும். ஸோ இதெல்லாம் பார்த்தீங்கன்னா அதோட கவுண்ட்ஸ், ஓகேங்களா? இந்த 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 பாரோட கவுண்ட்டு, அதான் நம்ம ஃப்ரீக்வன்சி டேபிள் எடிட் பண்ணுவோம் இல்லையா.
ஸ்க்ரீன் ஷேர் பண்ண முடியுதுல்ல?
யா எஸ். இப்போ ஓகே விளங்குது தானே சார்? இதில் வந்து இந்த இந்த என்கிட்ட வந்து ஸ்பைடர் 4 ரன் ஆகுது, இதில் ஸ்பைடர் வெர்ஷன் 4. அப்போ
ஓகே, கொஷின்ஸ் வணக்கம் நண்பர்களே. இவ்வளோ நாள் வந்து நம்ம வந்து தமிழில் செஷன்ஸ் பார்த்தோம். சேம் டாபிக்ஸ் லைக் ஸ்டாட்டிஸ்டிக்ஸ், மிஷின் லேர்னிங், டீப் லேர்னிங், ரெயின்ஃபோர்ஸ்மெண்ட் லேர்னிங், நேச்சுரல் லாங்குவேஜ் ப்ராசஸிங், இதெல்லாம் வந்து தமிழில் டாபிக்ஸ் பார்த்தோம். இன்னைக்கு தட் இஸ் நவம்பர் 13th ஜான் 3rd வரையிலும் வந்து பார்த்திங்கன்னா இங்கிலீஷில் கம்ப்ளீட்டாக வந்து நம்ம பார்ப்போம். இங்கிலீஷில் வந்து நம்ம பார்க்குறது பார்த்திங்கன்னா சேம் தான், லைக் ஜூம் மீட்டிங்கில் தான் நம்ம கனெக்ட் பண்ணி பண்ணுவோம். மீட்டிங் ஐடி, பாஸ்கோடு, டைமிங்கு எல்லாமே வந்து நான் காட்டுவேன். நீங்கள் அதை பார்த்துருங்க. பார்த்துட்டு லைக் வி வில் ப்ரொசீட் வித் தட். இனிஷியலாக வந்து நம்ம சேம் தான் ஸ்டாட்டிஸ்டிக்ஸ் ஆரம்பித்து நேச்சுரல் லாங்குவேஜ் தட் இஸ் ஸ்டாட்டிஸ்டிக்ஸ் முடித்ததுக்கப்புறம் பைத்தானுக்கு அப்புறம் மிஷின் லேர்னிங், அப்புறமா டீப் லேர்னிங், அப்புறமா வந்து நேச்சுரல் லாங்குவேஜ் ப்ராசஸிங் ஒரு 2 செஷனு, அப்புறம் வந்து பார்த்திங்கன்னா தட் இஸ் ரெயின்ஃபோர்ஸ்மெண்ட் லேர்னிங் செஷன்ஸ் பார்ப்போம். இதில் பார்த்திங்கன்னா லைக் எல்லாமே வந்து எல்லா ரெக்கார்டிங்கும் பார்த்திங்கன்னா நம்மளோட சேனல் bigdatahands-on.com சேனல்ஸில் டெய்லி. இது வந்து உங்களோட ஐடேட் டைமிங் பார்த்து 1, அப்புறம் தினேஷ் வந்து அப்பப்போ உள்ளுக்க செஷன்ஸில் வருவார். ஒரு சில செஷன்ஸ்க்கு அவரும் வருவார். அதில் வந்து நம்ம தமிழில் செஷன்ஸ் எடுத்துட்டோம். இப்போ வந்து முழுக்க கம்ப்ளீட்டாக வந்து இங்கிலீஷில் இருக்கும் செஷன்ஸு. பார்க்கணுன்னு நினைக்கிறவங்க எல்லாமே வந்து ஜாயின் பண்ணிக்கலாம். ஈவன் வந்து நம்ம தமிழ் ஆட்களும் வந்து இன்னொரு தடவை செஷன்ஸ் வந்து பார்த்தோம். இன்னையிலேருந்து லைக் நவம்பர் 13th வந்து கொஞ்சம் ஜான்வரி 2nd, ஜான்வரி 3rd வரையிலும் புஷ் ஆகிருக்கு. நீங்கள் ஆர்வமுள்ள நண்பர்கள் யாரும் இருந்தீங்கன்னா தயவு செஞ்சு யூ கேன் டேக் பார்ட் இன் ஆர் செஷன்ஸ். இங்கிலீஷ்லேயும் இதை வந்து நான் சொல்லணும்னு விருப்பப்படுறேன். ஹை லேர்னிங், டீப் லேர்னிங், and the timing, log on, like if you want to know about us, you can go to our website bigdatahands-on.com. போர்ட்ஸ்ல மீட்டப் வீடியோஸ்ல இங்க போஸ்ட் பண்ணுவோம்.
Python இப்போ எது நெட்ஃப்ளிக்ஸ் யூஸ் பண்ண
ஹாய் கைஸ் வெல்கம் டு த
நெட்ஃப்ளிக்ஸ்